So we're finding the volume inside of this hyperboloid, defined by the equation x squared plus y squared minus z squared is equal to 1. They call it a hyperboloid of one sheet because they're two seemingly different graphs that are connected, right? Because you could have two separate hyperboloids, right? Or it's one hyperboloid, but in two separate pieces. That's the hyperboloid of two sheets, right? So it's just how they denote it. There's an etymology to that name, and it has to do with I mean, it's you got to kind of imagine a lot, but I mean, most people are familiar with the Mobius Strip. It's along those lines, but if you take one sheet, one sheet of paper, like infinitely length paper, if you were to wrap it up, right? If you were to wrap it upon itself, you'd get a cylinder, right? So one sheet of paper. I never have a sheet of paper when I need it, but you've seen that demonstration before, where you take a piece of paper and you just kind of bring the edges together and it forms a cylinder, right? What they're saying here is, with that one sheet of paper, you can create this figure if you pinch it from all directions at in this case to the origin. All right. The hyperboloid of two sheets, there's no way you can do that with a single sheet of paper. You'd have to use two separate sheet of papers. So I'm sure you've also done the maybe in geometry class, maybe the teacher, to amuse you on a day where maybe you're like day before a break or something. It's like, oh, look what we could do with some paper, something along those lines. And so, we're pinching it together around the origin. If you zoom out the right way, it'll look like it's coming to a point. Kind of looks cool. But I'm sure you've also taken a piece of paper and made a cone out of it. Like where you start off with the cylinder, but then you pin the bottom and let the top open up. And try to keep it as closed as possible, but you open up the top more than you have. The bottom is to a point. So with a single piece of paper, you can come up with just a single cone. But if you wanted to have those two disconnected cones, you'd have to have two sheets of paper. Right? So there's more to it than that in terms of a proof, but that's just the quick justification for the etymology of the name. So anyway, we need to find the volume inside of this thing. Now, we have concerns, all right? Because we're doing this over the interval of -2 to 2, which is fine. You look at my graph here, in order to make it look like what's on the paper here, I zoomed out, so it's like -20 to 20, right? So a couple of things is based off of the misleading nature of, and I'll just bring it back to home and then bring it in from there again. The misleading nature of this graph, the diagram that I have on the paper, makes it seem like it comes to a point at the origin. Same graph, typed in the same thing. I just zoomed out like insanely. All right. Here, I'm zoomed in. Maybe not insanely, but I'm zoomed in. All right. They're saying to figure out the volume inside of this hyperboloid, but only on the interval of -2 to 2. That part is easy enough, because we're going to max it out at a height of 2 for z, and you could even plot that z equals 2. All right, so capped between z equals 2 and z equals -2. All right, so let me bring it out a little bit more so you can see. All right, so there's a little smidge of hourglass in between. That's what we're looking at. All right. It's symmetrical, though. So what does that mean? Well, it means that if we figure out the part that's between 2 and the xy plane, then we could just double that and figure out the equivalent value between the xy plane and -2. All right. So depending on the coefficients, the hyperboloid may not be symmetrical, but in this case, it is. Right? And there are ways to prove it, but when it absolutely looks symmetrical, it's a good place to start. All right. So one thing that you could do if you wanted to quote unquote prove it, it's not really a proof, more like a demonstration, is substitute the bounds into the function. So x squared plus y squared minus z squared is equal to 1. All right. If I plug in a -2 squared, a -2, and then square it, I'm going to get x squared plus y squared minus 4 equals 1. X squared plus y squared is equal to 5. Right? If I do the same thing, but with a +2, right, it's going to give me the same stuff. Same expression, same equation, same shabiggity bangity boomity boom. All right. So these two circles are going to be equivalent. If you want, you could just make the cylinder that is the that jumped on me. You can make the cylinder that is the extrusion of this of the circle x squared plus y squared equals 5 into 3 dimensions, and you can see that it's I turned it. What did I do? I just deleted it. What did even happen? Nobody knows. I know what happened. I mean, I hit delete. I don't know how I mistakenly hit delete, but I did. All right. So you're looking at something that's bottled up completely. You bring it out further, it's easier to see. You do have that symmetry. All right. Now you could do a test for symmetry. Right? Negate the z value. If your function is exactly the same as what you started with, then you have symmetry. I mean, it's just like that old pre-calculus rule that nobody ever remembers. But I mean, you could do that. But this is a good. I mean, I think we've kind of convinced ourselves that we're looking at a symmetrical relationship. Right. So what we're going to do is find the volume, again, contained between z equals 2, right, z equals 2 and the xy plane. Right. We just need some bounds. Right. Now, there is one little nugget that's going to be at issue here. Right. And that is, now I got a big old mess going on here. There is a component of this graph that exists on the xy plane that's not just equal to 0, even though it looks like it is in the case of the two opposing cones on the paper. There's a circular space in the xy plane. Right? So if you remember, when you're finding the volume using the double integral technique, you're finding the volume beneath the surface or between the surface and the xy plane. Right? So if you think about what that would mean, well, you only have certain parts of the surface here that would actually, make sense to double integrate. All right, let me actually bring this one in because it's going to be easier to mark up. I don't even know what I hit. I don't know. That just refreshed on me. I could take this one and crop it. So what you're going to get it's only from -2 to 2. So let's say 2 is right around here. All right, so let's say that z equals 2. You're only going to get this outer fringe and the corresponding outer fringe on the other side. All right, so that's what it's going to give us. All right, because it's hollow. There's nothing to be contained beneath in terms of the surface, the surface that represents the hyperboloid of one sheet. Let's see if recover works. Oh, kind of worked. Gave me something back. So what do we do for the inner piece? Well, that's actually probably the nicest thing that could happen to us, right? Because this inner piece here is cylindrical, right? So we could actually just hollow that out, right? So we would actually get, sort of along the lines of what we need to get if we take that out. But if we want, I'm sorry, add that in. We need to have that in. But a better way to handle it might be to take, let's see if this shows up halfway decently, the volume of this entire cylinder. All right, so find the volume of this and then subtract off those green little bits of schmutz there. All right, if we do that, then what we'll have is that hollowed out volume inside. All right, it's still potential space and we need it. That's part of what the question's asking us for. All right, so if we can do that, then we'll be in good shape. Now, you don't need to necessarily do a double integral to find the volume of a cylinder because it's a known geometric figure. Right, but in the spirit of the problem, I'm actually gonna do it that way. But on a test, if you wanted to do the double integral for the green part, but then use pi r squared h for the volume of the cylinder, that's fine. All right. So as long as you got your double integral in there somewhere, that's really what I'm after. All right, demonstration of knowledge and skill as well. That's all I ever ask. All right, so we'd be looking at double integral, goes all the way around, so 0 to 2 pi. Going from, well, now this is the big thing. It's like going from what to what? Well, if I want that whole cylinder, I'd be going from the center, so 0, to whatever the equation is that represents this circle. All right. Fortunately, we already figured that out. All right. When we substituted in a 2 for z, we actually found the equation of this circle. So this equation is x squared plus y squared equals 5, which in cylindrical coordinates is r squared equals 5. Converting or simplifying to r equals radical 5. All right, so we have our upper bound. All right, it was there all along. If we weren't looking for it, we wouldn't have necessarily realized it, but fortunately we did. All right, so 0 to radical 5. All right. So we're capping this at z equals 2. All right, so z equals 2. That's easy enough. We don't even have to convert that. All right, that's just a constant value. All right, it's always z times r dr d theta. If z were in terms of x and y, then I'd have to convert it over into polar coordinates, but it's constant, so I'm fine. All right, r dr d theta. All right, and so that's the cylinder. Now I have to subtract off the volume contained beneath the hyperboloid of one sheet. All right, so it's going to be another double integral that we're going to have to subtract off, going from 0 to 2 pi, because again, it goes all the way around. All right, now this one actually starts, if we're looking at this graph carefully, it starts, and I gotta get a different color in here. Let's see. Maybe there's orange. It's starting here and working its way out to this location. All right, in terms of the R value. All right. So the closest R value is related to, well, whatever that location is. The furthest R value is going to be the R value corresponding with this location, which we already determined is radical 5. Right? So at least we have the top bound, I should say. All right. But this inner circle here, I need that. All right. So I can get that by finding, based on the original hyperboloid, x squared plus y squared minus z squared equals 1. Replace the z with a 0. X squared plus y squared equals 1, which means r squared is equal to 1, which means r is equal to 1. All right, so the low bound is equal to 1. Square root of 5 is bigger than 1, so we're good there. The z corresponding to the hyperboloid of one sheet. Okay, well, we need that. All right, so z, let me just move this down a little. It's going to come from this equation, x squared plus y squared minus z squared is equal to 1. All right, I'm going to add the z squared to both sides, subtract the 1 from both sides, so z squared is equal to x squared plus y squared minus 1. Take the root of both sides. Now, it would normally be plus or minus. I only care about the top half, all right? Now, if I wanted to work the bottom half, I could, then I would incorporate the negative, but we don't need that. All right, so x squared plus y squared minus 1 is what this z would be for just the top half. Now, in polar coordinates, and we could have made the change earlier, but it 6 of one, half a dozen the other. We're looking at the square root of x squared plus y squared is equal to r squared minus 1. All right, so that's what my z is equivalent to for the hyperboloid of one sheet, just top half. So I have the square root. Oh, terrible. How about we do it this way? And then we're going to have the r d theta. All right. This one would be definitely a little bit more challenging to do if you needed to figure out the final answer. But again, like I was saying before, it's not, not as much of a priority, because ultimately what we're trying to do is learn the skill of coming up with the double integral. I'm trying to make this look halfway decent. Coming up with the double integral or sum of double integrals that could be used to find the volume. Because again, I mean, you use Desmos, you can use whatever. As it turns out, for most of these cases, and I'll tell you, in more times than not, if you are using the correct coordinate system, like if it's most appropriate to use a polar coordinate system, and you're using polar, cylindrical polar, then you should end up with an integral that's very calculator friendly. All right. It's when you try to use rectangular. So the very last step here, of course, would be to multiply the entire thing by 2, because we only have the top half. Right? So it's just a matter of taking this whole shabiggity bangity boom and slapping a 2 in front of it.